All right, so next speaker is Remy Dubertrand from Northumbria University, who will talk about ergodic and non-ergodic many-body dynamics in strongly nonlinear lattices. Remy.
Thank you. Yeah, I would like to thank the organizer for giving me the opportunity to present my work. To make the long story short and maybe spoil for those who plan for a nap, the idea is that I would like to present a model, and I strongly believe that the tools that you are usually using could be very relevant to help me better understand this model. And I will try then to first motivate this model, and then to discuss with you where the overlap can be. So the main question I'm interested in can be phrased in a physical way as follows. So what is the long-time asymptotics of a highly excited initial state in a large but finite quantum system? So the trick in this sentence is large but finite, in a sense that we know that if we push the size of the system to infinity, and if we look at what happened locally, then we can take the infinite part of the system as a reservoir, and the small part we are looking at as the probe. And this is where we expect thermalization or equilibration. But these ideas have been are being intensively discussed in the physics literature, basically, I would say, mainly from experimental reason. So there has been a very, very important experimental progress to basically isolate systems and then to control the size of them, to probe or understand what are the conditions to have normal thermalization or equilibration. So I chose these experiments when basically they are building a quantum version of the Newton's cradle. So you start with a wave packet of cold atoms, and you launch half of it to the left, to the right, half of it to the left. And basically there is no dissipation. There is no, I mean, you have half of the system moving and the other half could be the reservoir, but it's just as big. So it cannot be a reservoir. And basically, these things are non-interacting and oscillating for a very long time. I mean, much longer than any characteristic scale. And this is basically a behavior which is not what we expect as thermalization. And I wanted also to stress that this is also of more current interest in experiments when you have some cold atoms which are, when you put energy in the system to drive them away from thermalization, but you manage to slow thermalization without heating the system. So if you usually put energy in the system, you would heat it. But here you can see in red that the total amount of energy per particle remains roughly constant, whereas the thermalization is slowed down. So that's the motivation. So how to address this question? Well, for today, unfortunately, I will be only able to deal with classical system. I have some idea about the quantum system. I'm happy to discuss that at the end if you want. So to set the stage, we are looking at a physical system which is mainly described by a Hamiltonian. And this Hamiltonian is defined as a 2D dimensional phase space. And so the Hamiltonian flow is defined in the usual way. And in order to understand thermalization, I think the main idea, which again is a textbook approach, is to say that thermalization occurs if the Hamiltonian flow is ergodic. So I need to define what ergodics means. So I take an observable, so the quantity, the average, for example, I want to compute or think about if I have a certain field. Well, here this will be with a finite number of sites, but if I want to compute some average of the field, so this will be my observable. And the Hamiltonian flow is ergodic if basically for almost all initial conditions, the time average on the left is equal to the ensemble average to the right. So it is very important at this stage that I don't distinguish between integrable or chaotic dynamics. I'm going to do it exactly now, because mathematicians, for example, would say that you can have ergodicity also for integrable system. And what is the main ingredient is that your, what I call the invariant measure here, will be very, very different. If you have an integrable system, the invariant measure are measures basically supported on invariant tori. In particular, they are supported on submanifold of the phase space, which has a clearly smaller dimension as the full phase space, which is 2D. So for me, ergodicity will be, when I talk about ergodicity, I mean ergodicity on a submanifold, which has dimension 2D minus 1 or codimension 1. So I am excluding other conserved quantity. Ergodicity for me will be ergodicity without other quantities. Okay, so how to get ergodicity? And there are two strategies, I think, quite different depending on the dimension of the phase space. So if you talk about small dimensional phase space, I think this was actually the idea of Fermi, Pasta, and Ulam, so clearly not a new one. This was to say that, okay, we can achieve ergodicity by taking an integrable Hamiltonian H naught, and then you perturb it via a small parameter epsilon, and you expect that this integrability will be broken, and you will have ergodicity in the meaning I've just said. So here I just would like to remind that there has been a very, very important theorem in the 20th century to say that this is not true because the invariant structure, the two-dimensional, the d-dimensional tori will actually survive under small enough perturbation, and this is the KAM theorem. So in order to achieve ergodicity, I would like to invite you to play another game, which is called billiard or dynamical billiards, and this is the following. So I choose a shape here in the plane, and I start with the following. So I have a particle, one particle here, starting at p0. The magnitude of its velocity is 1. And I play the billiard game when I launch it following a direction I choose, and it goes along straight line or geodesics if you have curvature. And basically when it reaches the boundary of the domain, you apply optical reflection or specular reflection rules, which means that the incoming angle is equal to the outgoing angle of the trajectory. So after one impact, you, for example, reach P1. And you can continue like this with several reflections. And actually, it's quite elementary to see that in order to fully reconstruct your trajectory, you only need the location of the impact point along the boundary. So here I chose some origin to define my curvilinear abscissa along the boundary. So S1 is the abscissa of this point, S2 that point. And then you need the angle to basically describe the incoming directions toward the impact point. And with all that, you restore fully any trajectory. And actually, again, this is a well-known idea which has been explored. I mean, this is very visual in a low-dimensional phase space, because if you plot the curvilinear abscissa as a function of the cosine of the angle, which are canonically conjugated, you got in a bounded domain a very clear indication whether you are dealing with integrable dynamics. So then you will have smooth curve due to the foliation of the phase space, or if you have a cloud of points, and this will tell you about the presence of chaos. So billiards have been very, very important because you can have very different dynamics when you change the shape of the domain. So I was showing you the ellipse, which is one of the very, very particular examples when you have integrable dynamics. This is also the case for the rectangular billiard. Then you have a very few amount of triangles. When you move to most of the triangles or parallelograms, then you have something which I will call weakly ergodic. I can elaborate, but maybe not now. And but also what is very important is that even if it's low dimensional phase space, you can have full chaos. And this is an example when you have, for example, here, the what is called sometimes the Bunyamovich stadium. when you have a rectangle and you glue two half discs along the smallest sides. And you have also the sinh billiard when you put a circular obstacle inside the square. And for example, here I'm showing for you the Poincaré surface of section. So for the elliptical billiard, you have two types of orbits, typically trajectory, two types of trajectories. So one trajectory will follow the boundaries inside some annular region, and they are called whispering galleries. The other type of orbits will go across the segment between the two foci, and they are called bouncing balls. And you can see that you can see it nicely on the Poincaré surface of section via two different type of curves. And if I do the same recording of one single trajectory along this billiard, I have a cloud of points over all the available region. So this is what I call ergodicity. So this was ergodicity for small dimensional phase space. For large dimensional phase space, as far as I'm aware, this is quite an active research area in KAM theory, in particular to translate the KAM theorem in large but mainly infinite dimensional settings. And well, as we are talking about statistical physics, I'm not sure I need to elaborate more, but clearly this is very important if we want to talk about statistical mechanics, because the liter of air in this room contains basically 10 to the plus 23 particle, at least following my my last estimate. And then the main approach, if we want to start from a micro description and want to go into an emergent law, we need to assume the ergodic principle that a typical trajectory will be ergodic in the system. Typical is that, yeah, of course, this is the devil world. The typical means that I can have a some Hamiltonian can be mixed. So you will have some regular subregion in the phase space, and typical means that you would like to average over the initial condition. You would like to have a trajectory whose initial condition is basically not too far from the average over initial conditions. So if you have some regular subregion in the phase space, you don't want to look at those trajectories when the dynamics will be trapped even for a finite amount of time or for an infinite amount of time in there. Does that make sense? Okay. Okay, so back to the main question. Long-time asymptotics of a highly excited state, but now I'm looking at classical system. So again, the physical approach, and we heard about it. So fortunately, I can go a bit quicker on that. Is that we heard about it via the wave turbulence approach. So this is exactly what I mean by building a kinetic theory, formulating an H theorem, or having a hydrodynamics approach. And I think we will also hear about it at least tomorrow. So this has been the mainly physical approach, as is the one I'm aware. On the mathematical side, I'm only aware of one single system when the ergodic principle can be proved. So this is the Lorentz gas, basically. When you have one particle, you can map your many-body system in a one-body problem when one particle of the gas is basically trapped inside the signal billiard. And for them, it has been shown already some time ago that the time dynamics, the long-time dynamics is, the time average is coinciding with the ensemble average. So for the rest of the talk, I will, to be conservative, let's say, I will mean by thermalization energy equipartition, and basically this is closely related to ergodicity in the sense that I defined earlier. And some questions that are very interesting are how to fail thermalization. Again, there has been some intensive work, so especially to talk about disorder, to talk about the choice of the initial state, so related to Herbert's question already. And also, okay, a clear way to fail thermalization, in my sense, is to be integrable. So I want to consider a classical nonlinear chain, and I want to know whether it thermalizes, how does it happen, and what can lead to failure thermalization. So I could usually motivate it or relate it to Fermi pasta and Ulam, but I think Miguel helped a lot by giving a very nice introduction to it, so I will just skip that and get to our model. So I told you that billiard systems are very convenient to get chaos in low dimensional phase space. For large dimensional phase space, there has been ideas to get inspired from the billiard dynamics to get the idea of billiard dynamics into a chain. And so they have some interesting names. So there was the Dingeling model, which was actually, so this is a model when you have a linear chain, but you impose a hardcore interaction. And basically this model was introduced to see the standard Fourier law in the one-dimensional chain, because there was already a debate about why Fermi pasta Ulam failed Fourier law. I mean, with the numerical capacity of that time. And there was a follow-up model called the ding-dong model, when here again you have some billiard condition which is indicated there, that you impose a distance between any two adjacent particles along the chain. And for those two models, which have some, which are inspired by billiards, you have Fourier law, which was checked. So this is our model. So our model is defined by the probably the simplest Hamiltonian one can come up with. So this is an Hamiltonian which describes a chain of n sites, capital N sites. You have the normal sum between kinetic term and interaction term. So there is only nearest neighbor interaction. And the twist comes from the fact that the position vector at each site has a lowercase n-dimensional vector. And this position vector obeys billiard dynamics at every single site. So the position vector has to be included inside the domain. And I impose the normal specular reflection at each site. So two examples that we started to study for our model. The first one is the simple situation when you take that lowercase n is 1. So you have a scalar variable at each site. And the billiard problem will be just a 1D box. So you say that every position at your site, every position variable at your site is a real number which has to be between 0 and 1. And then you have the other version when you have a two-dimensional position vector at each site, and you can, for example, trap it inside a chaotic billiards. And for example, this would mean that you have a lattice field theory when you have chaos at the lattice scale. That's the construction. Another thing which I'm happy to develop if needed is that the model doesn't, the model is here to accept any shape of D. So in particular, we can impose every symmetry on the field. I mean, if I take a scalar field and D is the range -1 and 1, I have a Z2 symmetry at site. If I take lowercase equal to a two-dimensional vector at site and D being the unit disk, I have an O2 symmetry on the field. So this model should be related to existing model, clearly. I mean, it has the same, it's just the choice of D, I think, is a very huge opportunity to have, to show different situation. And yeah, to make the problem well posed, we need to impose overall boundary condition on a chain. And in our numerics, we chose periodic boundary condition to make the problem well posed. Okay, so what are the main features of our model? Well, the equation of motions are linear, dynamical equation. But again, you need to be aware that all the complexity, all the spice are coming from here. Our model is not a perturbation of a linear model. That's why when I say I ask for your help, I'm afraid that I will probably discard the help for the wave turbulence people because I'm not sure how I can make it weakly dispersive because there are hard walls and the walls are just hard. That's what they are. It's not analytic or smooth, exactly due to the presence of the wall. For generic choice of the domain, there is no translation symmetry, so there is no total momentum conserved. But it is an Hamiltonian system. It is easy to show that the reflection along the boundary conserves energy, so the total energy is conserved. And this is the only one. For generic D, this will be the, generic D, sorry. This will be the only conserved quantity. So there are two limiting cases if you look at the average energy per site. So if this average energy is very large, if you go back to the Hamiltonian, so each of the position vector is trapped inside a domain, which means in particular that it has a bounded norm. So if you take an average energy, total energy, which is very large, it has to go into the kinetic contribution. So if you take a very large initial energy, then it means that, or energy density, then it means that the interaction term is negligible, and you have just, in a good approximation, you have just a bunch of particles in a box which are almost non-interacting. If the energy density is very small, you can think about having a linear chain, which is only at distant times, you will fill the wall during one reflection and then carries on with a linear free dynamics. So, does the model thermalize? I think the honest answer I can give is, I don't know. And I will try to argue why. Okay, I should say that my answer is yes, with some level of confidence. I will try to articulate why, but I think that the question is actually more interesting than that. The reason is that one can try to look at this problem via two quite different routes. Either we take the lattice model of n sites with hard walls and send the number of sites to infinity, or we could write a continuous field theory with now smooth walls and take a hard wall limit. And as of today, I think it's reasonable to expect that they should give similar answer or the same answer. And well, again, I want to argue that this is more interesting. So if I want to take a chain for a large number of sites, and I want to look at the dynamics, a very common indicator of chaos, presence of chaos, is to measure the Lyapunov exponent. So you measure the Lyapunov exponent, actually not the Lyapunov exponent, but the Lyapunov spectrum, so the collection of all the Lyapunov exponents. So we did that for very long trajectory, and the different colors correspond to different numbers of sites. So the smallest number of sites should be 5, and then red, when you have more points, correspond to 30 particles. So the dimension of the phase space is 2 capital N. So if you increase the number of sites, you also increase the number of Lyapunov exponents. And in our case, so this is for small energy density, the unit energy density, large energy density. And we saw, at least numerically, that the smallest Lyapunov exponent was always positive, which means that if all the Lyapunov exponents are positive, our system is chaotic. So for those who are more familiar with the Lyapunov spectrum, of course, this is a Hamiltonian system. So of course, there is a second collection of Lyapunov exponents, which are just the mirror image of this spectrum and just with the negative value due to the Hamiltonian dynamics, but I just discard them because, for example, if I want to evaluate the Kolmogorov-Szenario entropy, I only need to look at the positive part of the Lyapunov spectrum. So, of course, we are dealing with a phase space of, for example, 60 dimensions, which is very, very difficult to sample. But in our case, for the collection of initial boundary conditions we could explore and the duration of time we could explore, we found a clear indication of ergodicity and actually hyperbolicity here because the Lyapunov exponents are all positive. And we can actually, I can argue a bit further about why it should thermalize by, I was telling you that thermalization in my case is defined by energy equipartition. So, well, let's try to compute some averages. So if I introduce the partition function for temperature that I introduce or via the inverse temperature beta, so this is the definition of my canonical partition function. And the difficulty here is to evaluate the multi-dimensional integral over the position variable. And it is usually powerful to use a transfer operator formalism. So you have to look at the eigenvalue of an integral equation, which I've reproduced here. And in our case, as it is so explicit, we can actually derive the equipartition of energy, which means that the average amount of energy per number of sites is equal to T over 2 times the number of quadratic degrees of freedom. And this agrees indeed with the two relevant limits, large temperature and low temperature. We actually did a bit more than that. So we looked at the 2-point correlation function, and we wanted to compute it via two ways. So the 2-point correlation is described by this. So you look at, for example, you can look at this bracket being the time average. So you have a certain initial condition and you propagate it further, and you look at this quantity average over the site, which gives basically the amount of correlation between, for two sites at the distance I. Or you can equally evaluate this quantity by doing an ensemble average. So this is what we did here. So the dashed line is the ensemble average, and these color lines are three different time average for growing size of the chain. So this is 20 size, this is 100 sides of the chain, and you can see that when we grow the size of the chain, we come further and further to the ensemble average, which makes us believe that yes, there is ergodicity if we look at this special observable. We could further use more refined asymptotics using the transfer matrix operator to actually deduce the second critical exponent, to have all the critical exponent for the phase transition at t equal to 0, and we recover the standard universality class for two-dimensional field theory. I would like to, I know I'm running a bit out of time, I'm sorry, but I would like, because I think this is now the relevant part for more integrable people. So the second route was to smooth the walls and go for a continuum field theory. So I rewrite the Hamiltonian, I remove the billiard condition, but instead I put a trapping potential, which is a smooth function. I've chosen this function, and I will tell you in a minute why. And this function is exactly is a potential function, which is forcing in the limit of large alpha the position x to be in between 0 and 1. This Hamiltonian now is analytic. It's absolutely smooth. And we can, in particular, use this smooth Hamiltonian to go to the continuum limit by increasing the number of sides and with a fixed length chain. So the positions now indexed by the site number becomes a field. And what I claim is that this is continuous for any finite alpha. Sorry, is integrable for any finite alpha. The reason is that if I look at the PDE, which is describing the time evolution of the field, I can do a simple scaling to actually recover sinh Gordon, for which we know this is integrable. The equilibrium properties are known since the 80s, and it was also one of the systems early used to write generalized hydrodynamics. But I claim that this is a singular limit, and that's why I'm coming to you to try to understand this large alpha limit, because, for example, I can write lax pairs for this PDE, and you will see that some of the coefficients will diverge. So if you have any idea in this direction how to treat that, I am very much interested. There are also some problem in the initial value problem, which I can comment on. But with that, I think I will just finish. Thank you very much.
Thank you very much, Bertrand. Are there any questions, maybe quick questions? Veer, yeah.
It looks like the order of limits doesn't commute. On one side you have a thermalizing model, on one side you have integrable. Do you have a sense of why that's?
So actually, I believe that they are commuting, but this one is much more tricky. I can only say it with words. I'm still working on that. My understanding is that this large alpha limit will be the same sort of limit when you go from KdV to Hopf. Well, if you can help me to prove that, I would be very happy, because that's my intuition at the moment, but I cannot prove it, because clearly alpha going to infinity, I have the free wave equation, but now the field has values constrained on the range. So here this will be between 0 and 1. So phi, xi and t are absolutely unbound, unlimited, but the phi, sorry, has to be between 0 and 1. So my question is there a way to, because I can write easily some solution which prove that, but again, there is more complicated scenario, in particular in the initial value problem that I would be happy to discuss. So,
thanks.
Thanks for the question.
Maybe I just make a quick comment for in many body system, ergodicity is a bit more tricky. And typically I don't know in your analysis, but you have time averages which will converge kind of much before the time that is required for the trajectories to cover the full kind of the full phase space. Phase space is very big. So for instance, in lattice models, quantum lattice model, you have mean square ergodicity even for integrable models. So yeah, I'm not sure how if you saw something like that in your analysis. But many body system is a bit more tricky to look at ergodicity. It's not necessarily the covering of the whole phase space. It's too big.
Okay, so you say that my definition of ergodicity is maybe too strong.
Maybe,
that's what you say.
Yes.
Okay,
so which
one?
Different. Yeah.
Okay, I'm happy to discuss about this. Thank you.
Anyway, thank you very much. Thank you, Bertrand, again.
Thank you.
So next speaker is Constance Schober. So Constance, if you want to share your screen and turn on your microphone.
Hello.